Mindsetters, welcome to Learn Extra Live. I'm Katleho and this is Natasha. How are you, Natasha?
Hi, I'm well, thanks Katleho. Nice to see you
Nice
again.
to see you too. I've been here for many Mondays now,
You
so
have.
we've been enjoying it. So as we know, we have finally reached the grade 12 show. And today, paper 1. And finally, for all you who have been wanting it, it's paper 3 as well, hey?
Yes, and grade 12s, obviously you're busy with revision now in the middle of prelims and all of that. So we're doing some nice exam revision for you this evening.
Okay, so thank you, Natasha. You can go over to your board. So guys, as you know, because it's Monday, we have some prizes. We have the Casio calculator as well as the Casio labeler. And as always, I don't even need to say this to you guys, but these prizes do go out to the most amazing, most fantastic, most excited, most everything mindset on the page. As you know, we have been posting up the winners for the past many weeks. So you know that it is very possible and very easy to win. You just have to want to, and you have to be involved. Our Facebook page is facebook.com/learnextra, and our Twitter handle is @learnextra. Thank you again to Liberty. Liberty has been absolutely awesome today, and I know your focus is going to be so high today because with prelims, with exams, with finals even, this show is imperative to you for passing. Over to you.
Thanks Katleho. All right, guys, so this is it. It's exam time. Well, it's an exam revision on the show, and we're going to look at paper 1 and paper 3. Firstly, we're going to start with a question from paper 1, a past exam, and most of you will know if you've been practicing exams, which you should be doing by now, that calculus is one of the biggest sections in paper 1. So we're going to look at a calculus question today, but specifically one that I know a lot of students seem to battle with, and that's the derivative graph. All right, so the first question we're going to look at is calculus derivative graphs, and then later on we will look in paper 3, we will look at a question on geometry, and if we have time, do a little bit more calculus, because as I said, one of the most important sections that you guys will be doing. All right, so let's get to it. So this question comes from the November 2010 paper, and hopefully you guys can read that. I will read it out to you, and I will try and get the graph and all of that in focus as we go on. Okay, so it says that the graphs of y is equal to g dash x. G dash x being the derivative graph, guys. So they tell you the derivative graph is ax squared plus bx plus c. Now, if you think about that for a second, if your derivative is giving you a quadratic function, then that means the original graph had to have been cubic. Because remember, if you take something to the power of 3 and you derive it, you're going to end up with an x squared. So therefore, the derivative graph is a parabola, as I will show you just now. So that means the original graph, g of x, must have been a cubic graph. All right. They also tell you that h of x is equal to 2x minus 4, so that's just a straight line, and they sketch both of these for you. And they tell you that the graph of g dash x, the derivative graph, is the derivative of a cubic function, but we'd already known that. Okay, they give you a few points. They tell you that they have a common y-intercept at the point E. C is the point minus 2 and 0, so that's one of the x-intercepts. D is 6 and 0, that's another x-intercept. And A is the x-intercept of H, which is your straight line. B is the turning point of G dash, and they tell you that AB is parallel to the y-axis. Okay, so this is basically what's happening. This is a graphical representation of everything that they have told you thus far. Okay, so let's have a look. E is your common y-intercept. You can see that. You've got B as the turning point of your parabola. D is the point 6 0, C is the point minus 2 0, and H is your straight line. Okay, so let's have a look at the first question. And this question, remember, is from the November 2010 paper. Okay, the first question for 1 mark, write down the coordinates of E. So guys, if you look at the graph, right, E is the y-intercept of both the parabola and the straight line. Now remember, how do you find y-intercepts? All you have to do is say let x be equal to 0. This one is actually nice and easy for you to do because they've given you the equation of the straight line. So they've told you that h of x is equal to 2x minus 4. So we can quite easily find the y-intercept from that graph. So h of x is equal to 2x minus 4. And remember that the y-intercept of the straight line and of the parabola are both the same. So therefore point E, okay, so this is question 1, and I'm looking at point E, which is the y-intercept. How do I find y-intercepts? You say let x equal 0. So in h of x, I'm going to say h of 0. I'll get 2 times 0 minus 4, and that will give me an answer of minus 4. So therefore, the coordinates of point E are, it's your y-intercept, remember, so the x value is 0 and your y value is minus 4. Okay, so the first question, nice and easy, just working out the y-intercept of the straight line, which is obviously going to then be the y-intercept of the parabola. Okay, the next question for 4 marks. Determine the equation of the derivative graph in that form y is equal to ax squared plus bx plus c. So guys, they want to now find out what the equation of this parabola is. Remember, this parabola is just the derivative of the cubic graph. And so this parabola itself will have its own defining equation. And they've given us a whole lot of information that will help us to find this defining equation of your derivative graph. Okay, so this is number 2. And we are working out the equation of g prime. Okay, so in the form ax squared plus bx plus c, and hopefully you all recognize that equation of a parabola. There's lots of different ways we could work it out. I'm going to use the one that you learned right in the beginning when you first learned how to work out equations of parabolas. We've got both the x-intercepts and we've got a point on the graph. Remember, we've just worked out that E is the point 0 and minus 4. So if I want to work out the defining equation of the parabola, I can use this formula. Y is equal to A times x minus x1 times x minus x2. All right, guys, and remember the x1 and the x2 here, those are your x-intercepts. When you find the equation of the parabola, you need to have your x-intercepts if you're going to use this formula. You'll also need another point on the graph, which we have. So we've got x-intercepts and another point on the graph, therefore we can use that formula. All right, so we've got y is equal to A. And remember, we don't know what A is, so the point of using this formula is to help us find out what the value of A is. Once we have the value of A, we'll be able to find the equation. So y is equal to A times x minus x1. Very important to use brackets here so you don't confuse your signs. x1 being the first x-intercept, which was minus 2. All right, and then your second x-intercept was 6. Okay, so it's x minus minus 2 and then x minus 6. The point that we have that we can use to substitute, the other point that lies on the graph, is 0 and minus 4. Okay, so I can substitute x is 0, y is minus 4 into this equation and work out the value of A, because now A would be the only unknown. So therefore I get A times 0, minus times minus is a plus, so this would just be plus 2, and then 0 minus 6. Okay, so I'm going to get minus 4 is equal to A. 2 times minus 6 is going to give me minus 12. All right, and then dividing both sides by minus 12, I will get that a is equal to a third. All right, so guys, we use that equation, y is equal to a times x minus x1 times x minus x2, to help us find the coefficient of x squared, to help us find the value of a. Once we've got a, we are not done, because remember they wanted the equation of g dash x. They wanted the equation of this derivative graph. So we're not just going to stop by giving them the answer for a. We now need to take that value for a and put it back into this line here so that we can times it out and get the equation. So we'll get y is equal to a third times x plus 2. And then we've got x minus 6. Okay, and let's just multiply that out. Okay, there we go. And I'm going to need a pen. There we go. So we get a third into x squared, and all I'm doing is just multiplying that bracket out. Plus 2x minus 6x is going to give me minus 4x. And then plus 2 times minus 6 will give me minus 12. Times your 1 over 3 into that bracket, and you're going to get a third x squared minus 4 over 3 x and minus 4. Okay, and in fact, when you get this y-intercept, it's actually a nice quick check for you, because remember the y-intercepts of both the graphs are the same. So if c is minus 4 in the parabola, and we know from the straight line we worked out that the point E was 0 and minus 4, so the y-intercept of the parabola being 0 and minus 4 matches up with the straight line, so we know that we haven't made any mistakes there. All right, okay, so we're going to go into the next one, which is writing down the coordinates of the turning points of G. Now here you've got to be careful, because remember we are dealing with the graph of the derivative. We've got G prime x, G dash x, okay? But now they're asking you for the turning points of the original graph. Now your original graph was a cubic function. So your original graph had the equation y is equal to a x cubed plus b x squared plus cx plus d. Remember, that's your defining equation of any cubic graph. Now, because we can already see that the gradient of this, or the derivative of that cubic graph, is positive, because look, we've ended up with a happy smiley parabola, which means the gradient is positive of the cubic function, your original graph would have looked something like this. All right, that would have been the shape. Okay, now guys, if you think about it, because remember, when you're trying to find the turning points of this cubic graph, what do? How do you find turning points? Okay, remember when you find turning points, you have to find the derivative and you make it equal to 0. So if I had the equation, if I knew what A, B, and C, and D was, and I asked you guys to find the turning points, then you would say, okay, well, to find the turning points, we say it's where the derivative is equal to 0. Okay, because when the graph is turning at that point, the gradient is 0. Okay, so if I wanted to find the turning points, I would say let the derivative equal to 0. But now we actually have the graph of the derivative. So where that graph is equal to 0, that's actually going to be the turning point of the original graph, y is equal to ax cubed plus bx squared plus cx plus d. Okay, so let's just show you this on our graph here. This graph of the derivative, okay, so this graph of g dash, we see that it is 0 at the point C, 0 meaning that the y value has to be 0, okay? It's 0 at the point C and at the point D. So in other words, the derivative is equal to 0 at x is equal to minus 2 or at x is equal to 6. Okay, so the derivative, because remember this is the graph of the derivative. So we're looking for where the derivative of the original graph is equal to 0, because where the derivative is 0, that gives us our turning points. So therefore, the derivative is equal to 0 at the x-intercepts. So that means that the original graph will have turning points at x is equal to -2 or at x is equal to 6. And that's the answer for that one. Write the x-coordinates of the turning points of G. And the answer there is going to be x is equal to -2 and x is equal to 6. And this is an important concept, so I hope you guys understand that. All right. Okay, we've got a few more parts to this question. I don't know if we want to just carry on with it.
Let's just take a break, and then when we come back, we can go through the question.
All right.
So guys, we're going to take a quick ad break. When we come back, make sure that you are 100% focused, because this is such an important thing to do in your revision. See you right now. Welcome back, Mindsetters. Remember that we are doing grade 12 mathematics and we're going through some past papers. This is a revision session, so make sure that your questions are relevant to the revision that we're doing right now, just so that you are getting so much more from this one section, guys. This is very important. Easy marks, but very important marks. So just make sure that you are focused, guys, because in this section, you can get literally every single mark and literally pass with flying colors. So make sure that you are 100% focused and ask anything that you need to ask on what Natasha is doing. If you do have the paper next to you, then maybe it's a good idea to look through it as well. Check what's there that's bothering you, and then you can actually send us the question. Over to you, Natasha.
Okay, thank you, Katlego. All right, guys, so remember we are doing a calculus question from the November 2010 paper. So in this section, what I would like is, if you have questions on calculus, please send those through. In the next half, we will look at paper 3, which will be geometry questions. But for now, if you have calculus or any kind of algebraic question that, you know, kind of gets you a lot of marks, because I know a lot of the times people start asking word problems. Now, I know that, you know, when you're in the exam and, you know, you see this word problem, it can really, really bug you down. But guys, it's not as much marks as calculus. So I prefer to concentrate on sections that are really going to give you guys a boost in the exam and give you some good revision to write paper 1. Okay, so for now, we're looking at calculus. All right, so we are on to part 9.4. Okay, we've just worked out that the coordinates of the turning point of the original graph G was going to be at x is equal to -2 and x is equal to 6. The next one is to now write down the x coordinate of the point of inflection. Now remember, the point of inflection is the point at which your second derivative is equal to 0. Okay, so point of inflection is where your second derivative is equal to 0. So how do we find points of inflections? Yes, we take the second derivative, equate it to 0, and then solve for x. Remember, we have the graph of the derivative already. We already know what the equation g dash x is equal to. We've got a third x squared minus 4 third x minus 4. So if I wanted to find the points of inflection of the original graph, I could derive this, because remember, this is the first derivative. So if I wanted to find the second derivative, I could just derive this equation here. But let's go to the graph and let's explain to you what's happening. Okay, remember, point of inflection is where your second derivative is equal to 0. Okay, so if we interpret that in terms of the graph that we've got, because remember, this is your graph of the derivative. So if I were to derive this graph again, right, that would be your second derivative. But remember, your point of inflection is where the second derivative is equal to 0. And on this parabola, where is the second derivative equal to 0? At the turning point. So therefore, when they're asking me for the point of inflection, they basically want to know the x value at point B, because that is where my second derivative will be naught. It will be at the turning point. Okay, so if I know the coordinates of B, then I will know what the point of inflection is. Okay, well, if I know the x value at the point B, I will know what the x coordinate of the point of inflection of the original graph is. Okay, all right. So how do I find point B? Well, it's at the turning point of the parabola, which means it's exactly midway between C and D. So therefore, to find the coordinates of point B, and this is number 4, to find the x value, all I say is it's the turning point of the parabola. So how can I find it? I'm going to say x is equal to exactly midway between the x-intercept, so minus 2 plus 6 divided by 2. So that's going to be 6 minus 2 is 4 divided by 2 is 2. So therefore the point of inflection of the original graph will be at the point x is equal to 2. So there is another way you could do it. This is the way we did it, showing the midpoints, because obviously the turning point of your parabola is exactly midway between the x-intercepts. So I added them and then found the midpoints of those two. The other way you could do it was to take your equation for your parabola, a third x squared minus 4 over 3x minus 4, and use the formula for your axis of symmetry. X is equal to minus b over 2a. You could have done it that way. Or if you preferred, you could have even taken this equation and derived it and then made it equal to naught and solve for x. Either way, you will get the same answer. Okay. All right, guys, the last part of this calculus question. Explain why G, now G, they're talking about the original graph. Explain why G has a local maximum at x is equal to minus 2. So, let's look at our derivative graph. Remember, at this point, x is equal to minus 2. It's where your original function is turning. It's the turning point of your original function, okay? And this derivative is naught at that point, okay? So, if we want to explain why it is a local maximum, now remember I've already shown you that because we're dealing with the positive gradient, this is the kind of shape that we're looking at for the calculus graph, all right? So, let's just explain it here. So, this is the graph that I'm looking at for the original function. This is the type of shape we're looking at, all right? So, this is because a is greater than naught, or you're looking at your derivative being a positive graph. And they want to know, why is it at x is equal to minus 2, how can we say that that is, or why is that a local maximum? Okay, so we can see that the graph is turning there at that point, and they want to know, why is it a local maximum? Well, if you look at the graph itself, all right, you can see that if you were to draw a line at this point on the graph and then another one on the other side, okay, those lines would have different gradients because they're doing different things on either side of x is equal to minus 2. To the left of x minus 2, of x equals minus 2, so if x is less than minus 2, and I'm looking to the left of that graph, we have a positive gradient. So for x is less than minus 2, we're looking at a positive gradient. So in other words, the graph is increasing. So the graph is increasing up to the point x is equal to minus 2. Then, at the point x is equal to minus 2, the derivative is naught. But then if we look beyond that point, so if we look from x anywhere to the right, so for x greater than minus 2, we have, if I had to draw a line to the graph, it will slope towards the left, so that means it has a negative gradient. And if it has a negative gradient, it means all the function values are decreasing to the right of minus 2. Okay, so if you have increasing values and then decreasing values after that point must be a local maximum. So therefore, because x less than minus 2, we have increasing values, and for x greater than minus 2, we've got decreasing values. This implies, therefore, x equals minus 2 is a local maximum. Okay, so it's a local maximum because we're going from increasing values to decreasing values, so that's got to be a maximum at that point. Okay, I think we're going to quickly do a basic derivative question and then maybe take a quick break before we go to paper 3 work. All right, and it's obviously one that you guys are familiar with. You've seen deriving questions, deriving by rule over and over again. All right, so let's have a quick look at that. We need to find the derivative dy dx if y is equal to, and they give you an expression. Now, some of the pointers that you need to remember. In order for you to derive, you need to have single terms. Okay, they need to be separated by pluses and minuses. Your x's should not be in the denominator. If you have x's in the denominator, you need to use your exponent laws and take them to the numerator. You cannot have x in the denominator when you're using your derivative rules. Another thing is you cannot have square roots and all of brackets and that kind of thing. You want things to be as simple as possible. So if you have things like a square root, once again, you need to use exponents to get that out of the square root. So the first thing we need to do here is to rewrite this, and the 2 is fine where it is because it's not an x, okay? There's no deriving that's going to happen to the 2, so that can stay where it is. The first term is fine as it is, x to the power 6 over 2, but we have a problem with this one because it's under a root sign. Now remember, root of x from exponent laws, if I want to take it out of the root sign, it's going to be x to the power whatever's inside the square root divided by that power there. So it's going to be x to the power of 1 over 2. Okay, so this is going to be 4 times x to the power of a half. Okay, and that rule, guys, I cannot stress enough how important exponents are. They come up in logs, they come up in calculus, they come up all over the place. So make sure you understand your exponent rules. But that law, root of x is equal to x to the half. It's coming from your exponent law. I'm just going to make a little side note here. If you've got a to the power of m, and we're taking the nth root, to get that out of the root sign, to write it as a rational power, it's going to be a to the power of m over n. Okay, so that's just a little side note of why we could write root x as x to the power of a half. It comes from exponents. If you've got the nth root of any number to any power, it's always that number from inside the base of the exponent is going to be raised to the power m over n. Okay, all right. So now that we have y in this form with separate terms, we can now use our rules for deriving. Remember, when you derive, you put in a prime sign, okay, to show that you are deriving. If you don't put that in, we don't know that you're deriving because it looks like it's still y. Okay, so you need to put that sign in to show that you've started deriving. From the rules for deriving, we're going to take the power of the x, bring it to the front of this x. So it's going to be 6 times 1, which is 6. And then from the power of x, we subtract 1. All right, and then this side's the same thing. It's going to be 4. Bring the power of the x, times it to the coefficients. And then from your power, okay, and I'm just going to have to get rid of this so I can get a little bit of space here. Whoopsie. Okay, from your power, you subtract 1. It's going to be x to the power a half minus 1. Okay, so simplifying that, 6 divided by 2 is just going to give us 3. x to the power 6 minus 1, which is 5. 4 times a half is just 2. And then x to the power a half minus 1 is just negative a half. Okay, you can leave it there, but sometimes they say write with positive exponents. Then we can rewrite x to the minus a half using, once again, your rules for exponents. We can write this as 2 over x to the positive a half, because remember, if you want to make a power, if you want to change its sign, you need to change its position. So it's in the numerator now. To make that minus a half positive, I need to move it to the denominator. So it becomes 2 over x to the half, which is 2 over root x. All right, so I think this is a good place for us to take a quick break before we get into paper 3.
Okay, awesome. And I know many of you have been asking for paper 3 questions. We promised you that we'd do it, so we will do it after the break. Make sure that you have everything ready. Ask questions, guys, on what is done. Don't bring new questions, because then what happens is that there's confusion. Like, some people are asking about this, some people are asking about that. So make sure that you ask on what Natasha is doing today. Your questions will be answered, but they may be answered in the next revision sessions. So just be patient, because we will get through all your revision, guys. We promise you. See you now. Welcome back, Mindsetters. I hope you guys had a great break, because we are now moving on to paper 3. Paper 3 always needs all your focus, guys, so make sure you're focused. And those of you who aren't really doing paper 3, I don't know if it's still an option. Hey, Natasha, it is an option to do paper 3.
Well, not if they haven't chosen it already.
Yeah, I know, but I mean, like, they had to have chosen it to do it. If you're not doing paper 3, guys, don't run away at all. Focus, guys, because there are some things that they go through that you need as well. So you need to be able to do this to even do your papers. So just make sure that you stay with us throughout the show, because we will be helping you out with lots of things. Over to you, Natasha.
Okay, thank you, Katlego. Guys, just to clarify, obviously paper 3 is a section all by itself. It's its own little monster. And if you're doing paper 1 and paper 2, you really don't need much of the information from paper 3. Geometry doesn't come into play there, not with the theorems and that. But, I mean, geometry teaches you so much of logic, like you're going to see today. And there are 1 or 2 things that you still need for paper 2, like remembering that when a radius meets a tangent, that angle is 90 degrees. Those little things you do need to know, okay? But if you're not doing paper 3, then this question is not for you, okay? All right, so geometry question coming from March 2011, which is the supplementary exam from the beginning of last year. And geometry, always a favorite topic. I love geometry. I hope you guys enjoy it, even though I know it's not everyone's favorite. Let's have a look at the question. And guys, remember, whenever you do geometry, the best way to, the way you're going to get the most marks out of it, or the most results, is to know your theory. Because if you know those theorems and you know when to apply it, it's going to make life much, much easier. But if you don't know those theorems, it's going to be incredibly difficult. So make sure you understand your theorems. All right. So they say in the diagram, they give you 2 circles which intersect at D and at B. All right. AB is a straight line such that it intersects circle BCD, circle BCD being this one here below at the bottom at point E, and BC is a straight line such that it intersects circle ABD, ABD being the one towards the left, and it intersects it at point F, and then they tell you a few of the lines are joined. They then tell you that angle F2 is 180 minus 2x, so that angle is 180 minus 2x. And they also tell you that FC, which is the length of this triangle FCD, FC is equal to FD. All right. I always find it very, very useful to just look at the information that they've given you and try and decipher and write as many things as you possibly can on the diagram. Also, try to identify cyclic quads. Remember, cyclic quads have all 4 points on the circumference of the circle. So try and identify cyclic quads. See if there's exterior angles of that cyclic quad, or if there's a circle center, look for angle at center, and also identify angles in the same segment if you do have cyclic quads. So let's have a look at the drawing and see what we can figure out before we look at the question. Okay, and for this I'm just going to swap to a different color. All right. Okay, so remember guys, I told you that F2 is 180 minus 2x and that FD is equal to FC. So that means that FDC is an isosceles triangle. If it's an isosceles triangle, the base angles are equal. So that means that D4 is equal to angle C. All right, so that's because FD is equal to FC, and angles of a triangle would mean that D4 is equal to angle C. So using angles of a triangle, because we've got F2, it would be quite easy to find D and C using the fact that angles of a triangle add up to 180 degrees. At this point, I also want to try to identify a few cyclic quads, because sometimes they seem easy to identify, but it can be a little bit tricky. So if we look at the circle that's towards the bottom of the diagram, okay, so we're looking at circle F, E, D, E, C, so that's the one here at the bottom. The cyclic quad there that we have with all 4 points on the circumference is going to be D to E to, what is that, B to C, and then back there. Okay, do you see that that is a cyclic quad? We've got 4 points touching the circumference, so therefore D, E, B, C is a cyclic quad. Okay, remember when you've got cyclic quads, there's things like exterior angle is equal to the interior opposite angle, those theorems that you've got to remember. So we've got one cyclic quad there, and let's look at the other triangle and see if we've got another one. Okay, sorry, the other circle, and see if we have another cyclic quad. You can see, and this is quite tricky, and especially becomes tricky when they've put two circles together. But this one, FD, whoopsie, just need another color there. Let's try that again. So FD, and then go from to B, and then across all the way to A, and then back here. Okay, so hopefully you guys can see that. BFDA is another cyclic quad. Okay, so the cyclic quads we've identified already are A, B, FD. Okay, and that's in that circle there. And then in the other circle we have cyclic quad D, E, B, C, and that's in this circle on the left. Sorry, on the right of your screen it would be. All right, so we've already worked out that FDC is an isosceles triangle, so we can use angles of a triangle to help us figure out things in that one. Let's look at the first question. Now that we've identified a few cyclic quads and we've got an angle in that given, let's look at the first question to see if what we've written down so far can help us. All right. They say calculate with reasons in terms of x, angle DEB. So if we're going for angle DEB, that's this one here. All right, that's going to be that angle E1. All right, so that's really the one they want us to work out. Okay, so guys, what I'm going to do is, this has helped us to identify, all these colors have helped us to identify the quads in that, but it's becoming a bit difficult to see which ones we're working out. So I'm just going to take off all of those colors and show you step by step as we do the working. Just remind you of what were the cyclic quads and the rest of it. All right. So DEB, remember we've identified that as angle E1. That's the angle that they want. It is also one of the angles of cyclic quads, DEB. EBC. All right. There's different ways we could work it out, but possibly the easiest one is going to be from the fact that they've given us that F2 is 180 minus 2x. So if F2 is 180 minus 2x, and I know that FC is equal to FD, that means I can work out the value of angle C and the value of angle D. So let's write down the proof to this. And this is 9.2.1, and this is part A. We're working out angle DEB. Okay, so the first thing we're going to do is to work out angle C. Why do I need angle C? Well, if you look at angle E1 and angle C, those are opposite angles of a cyclic quad. Remember your theorem. Opposite angles of a cyclic quad add up to 180 degrees. So if I know what C is, then 180 minus that will give me E1. Okay, and we do know what C is because we've got F2. All right, so this is now in triangle FDC. All right, we know that angle C is equal to that one, D4. And the reason for that, it's because they told us that FD is equal to FC. Okay, and it is important when you set up your geometry proofs that you put reasons. Hey, remember you do get marks for those reasons, so remember to put in reasons that make sense. All right, so angle C is equal to angle D4, and that's because FD is equal to FC. We also know that angle F2 was equal to 180 minus 2x, and that was given to us. Okay, so if I want to find C and D4, I can say in that triangle FDC, I know that F2 plus C plus D4 is equal to 180 degrees. How do I know that? Well, those are the interior angles of that triangle. So therefore, those are equal to 180 degrees, and that's because of sum of angles in the triangle. All right, we know what F2 is, and we know that C and D4 are equal to each other. So therefore, I can say C plus D4 is going to be 180 minus F2, which is 180 minus 2x. And that's going to give me 180 minus 180 will cancel out, and I'll just get 2x. So therefore, C plus D4 is equal to 2x, but C and D4 are equal to each other, right? So remember, all I can do here is I can literally replace D4 with C because they're the same thing. And then I'll get 2C is equal to 2x, therefore C is equal to x. All right, once we've got angle C as x, and then remember D4 is going to be exactly the same thing, well, angle E1 is just going to be 180 minus angle C because of opposite angles of a cyclic quad. So E1, angle E1 plus C is equal to 180 degrees, and that is opposite angles of a cyclic quad. Therefore, E1 must be equal to 180 minus C, and C was x, so therefore E1 is 180 minus x. All right, so I went through that in quite a lot of detail just to show you how you would build the proof up. So therefore, we've got now the value for E1, and that is 180 minus x. All right, so that's the first question. The next one says, calculate A. So there's A all the way there. So if you look at A, it falls into a few different triangles, but importantly, it falls into a cyclic quadrilateral. The cyclic quadrilateral that I showed you at the beginning FDAB or ABFD, all right? That one that we saw in that circle there. Okay, so if you look at that cyclic quad, all right, F2 is the exterior angle of this cyclic quad. Okay, so if we're looking at A, B, F, D being your cyclic quad, then F2 is the exterior angle of that cyclic quad. Therefore, we know that it must be equal to the interior opposite angle, because that's what the theorem says. F2 is going to be equal to A, because F2 is the exterior angle of cyclic quad ABFD. So therefore, since F2 is equal to 180 minus 2x, it means that angle A must also be 180 minus 2x. So A is going to be 180 minus 2x, and that's because exterior angle of a cyclic quad is equal to the interior opposite. So therefore A is going to be equal to F2 is going to be equal to 180 minus 2x. All right. So guys, I hope you are following this. It is a typical exam question. It's using all those different theorems that you know about cyclic quads. All right. So we're on to the very last part, which says, hence or otherwise prove that ED is parallel to BC. So ED and BC. Now remember, the way you can prove that things are parallel is by showing there's either alternate angles, corresponding angles, or co-interior angles. So remember, we know that this one is 180 minus 2x. That's just what we've proved now, because they said hence or otherwise. We've also worked out that angle DEB. What did we work out there? That one was 180 minus x. So we've got that 180 minus x. We've got that A is 180 minus 2x, and we want to prove that these are parallel. So we're going to either look for co-interior or alternate angles or anything like that that we can find. All right, so let's have a look. We know that angle E1 is the exterior angle of triangle. Now I'm talking about a triangle, hey, not about a cyclic quad. E1 is the exterior angle of triangle AED. Okay, now this is when that grade 9 geometry comes into play, because we know that the exterior angle of a triangle is equal to the sum of the interior opposite angles. So therefore, what that means, and I'm going to try and put the working on the top here so that we don't have to keep flipping down. Okay, so therefore E1 is going to be equal to A plus D, and the reason for that, that's because of exterior angle of triangle. All right, so E1 is going to be equal to A plus D1. So I know what E1 is. E1 is 180 minus x. I know what A is. A is 180 minus 2x. So if I want to find D, it's going to be angle E1 minus angle A. All right, and that will give me the value for D. So I'm going to get 180 minus 180. They would cancel out, and I'm going to get minus x plus 2x. 2x minus x is equal to x. So therefore D1 is equal to x. So if D1 is equal to x, now have a look at how this has helped us, because now that I've got D1, remember I was looking to either show if those lines are parallel, corresponding, co-interior, alternate, I can see that C is also x. So C is equal to D1. Since they're both equal to x, but if you look at the shape of that, we've got corresponding angles. Okay, we've got sort of this little F shape going on there. So C is equal to D1. Those two are equal, but those are corresponding angles. Therefore, so since these are corresponding angles, we can say therefore ED or DE is parallel to BC. Okay, because those were corresponding angles. All right, so we went through quite a lot of revision for paper 1 and paper 3. I hope that you guys benefited from all of that. Katlego, do we have any comments coming through?
I'm trying to check if we have some comments. For now, I don't think so. I think everyone's just really happy that they got to go through some paper 3. I think that is very important to them. Do you have anything that you want to say to them?
Well, guys, obviously keep revising, and exams that time when all you can do really is do as many past papers. Do as many past papers as you possibly can, all right? So I know everyone's in the middle of prelims and that, so just do tons and tons of questions, all right? And obviously send us any ones that you are having problems with. We will try to answer them. Okay, so for today, remember all we did is we went over paper 3, a paper 3 question which was on geometry using our theorems on cyclic quadrilaterals. And we also did, in the beginning of the lesson, we went over paper 1, which was calculus, and we looked specifically at the derivative graph. And remember that calculus is one of the biggest sections in algebra. So if you're really looking for a place where you can get marks, then that place in paper 1 is calculus. All right. So good luck and study hard, and we will see you next week. Back to you, Katlego.
Thank you, Natasha. So guys, I know that we couldn't go through all of the questions. I don't know, Natasha, if you can go back to that one question. I think someone just wanted to see the answer again on what you, the short question that you did.
Oh, okay. We can go over the, let's just find it.
Just the short question that you did.
The deriving.
Yes, the deriving.
Let's just see if we can find it.
If it's there somewhere.
I think it was here. It seems to have suddenly disappeared, Katlego. Let me quickly try and find it.
Yes, that's it.
There we go. All right, guys. So just a reminder of how we did this. Remember that with your deriving by rules, you need to have single terms. So that was really in essence what this was showing. You have to have single terms where there's no x in the denominator, there's no root signs, and there's no brackets. So what you want to always try and do is, if you have brackets, times them out. If you have a root sign, as we showed you in this question, you need to get rid of that root sign by using your laws for exponents. So in this question, the only little trick here was to change root of x to x to the power of a half. Okay, and remember we did that by using the laws of exponents. Once we wrote x as x to the power of a half, we got to a stage where we've just got separate terms. Once we've got single terms like these, we were then able to derive by rule. Okay, so the big clue there, have single terms so that you can derive. All right,
okay,
and good luck with the studying.
Thank you. So guys, good luck. Any questions that you may have, remember that Saturday is still a day, guys. We still have some Saturday shows, so make sure that you ask all your questions then. Remember to help each other as well, guys. Thank you to Liberty, and thank you for joining us, guys. See you next week, Monday, for some more maths. Bye, guys.